In this short presentation, I'm going to talk about how we'd like to do a seismic survey if we could, and then I'll explain why we can't do it that way and what we have to do instead. The difference between what we get in practice and what we'd like to have is where processing comes in. Processing turns the real data we can get into the ideal data we'd like to get. I'm going to explain this using this outcrop, which is Hartland Quay in southwest England. You can see a group of people at the base of the cliff near the cave mouth to give you some idea of the scale. And I hope you can also see some very remarkable folds. What would this look like on a seismic section? To start with, let's just mark in a few of the beds. So these will be the reflectors that we'll try and see on the seismic section. I'm going to concentrate on the left-hand end of this cliff. And I'm going to imagine putting a source of sound waves at the top of the cliff. Something that will give me a short, sharp shock. Maybe a sledgehammer, or dropping a heavy weight, or perhaps even letting off an explosive. When this source goes off, I'm also going to imagine that we're able to force the sound to travel straight downwards and in no other direction. At this point, that pulse of sound energy has reached the first of our reflectors. And I hope you can also see I've placed a receiver, a geophone, at the top of the cliff in the location where the source had been. And on the right hand side, I'm showing the recording from that geophone, our seismic trace. At this point, there's nothing on that trace because no sound has got back up to the geophone yet. But the sound has just got to the reflector, and some of the energy will be reflected. Most of the energy, however, carries on travelling downwards and now hits the next reflector, and we also get reflection of sound energy from there. So we now have two pulses of sound travelling back up towards our geophone, but neither of them have reached the geophone yet, and the trace still shows no signal. At this point, the first reflected pulse of sound has reached the geophone, and we see a kick on the trace. And now the second pulse has reached it, and we see another kick. Finally, the reflection from the bottom reflector reaches the geophone, and we get our final kick on the trace. At this point, we stop recording, and we have our first complete seismic trace. You can see 4 events on this trace corresponding to each of the 4 reflectors beneath the geophone. Now I want you to imagine that we repeat the whole thing again, but with the source and geophone moved along the cliff a little bit. That gives us another trace which we can plot next to the first one. And then we do it again, and again, and so on. The final result is a seismic section which can be interpreted, as I've done here, and I hope you can see that the blue lines I've put on the seismic section correspond to the white reflectors you can see on the cliff on the left. So that's how we'd like to do things, but it's not possible. It's not physically possible to do a seismic survey this way. So let's look at what the problems are. So here's my source again at the top of the cliff. So again, I let that off. But this time, instead of the sound just travelling vertically downwards, I'm being more realistic and allowing it to travel in all directions. So I'm showing here a wave front, a location where the sound has got to after a short period of time. At this point, the wavefront has got to the reflectors and is being reflected, which I'm showing with these dashed lines. And those dashed lines have now moved up towards the surface. The first one has actually reached the surface. The second one is still moving towards it. However, we've got no geophones. We need to put some geophones in. So let's start again, but with some geophones this time. You can see I've put geophones all along the top of the cliff, not just in one place as I did before. This makes sense. We might as well record as much information as we can. You'll also notice I don't have a geophone right next to the source. After all, it might be a stick of dynamite or something. So we probably can't put a source right next to it anyway. Now let's go through what I was just showing you, but showing also the recordings from all the geophones. At this point, the sound energy has gone down to the first two reflectors and we see the reflection coming back, as I said before. But you'll also notice that the original downgoing sound has gone past the first 5 geophones. And that's why the first of the traces on the right hand side have a signal. The kicks you can see there are the signals of the direct arrival, the sound that's gone straight from the source to the receiver rather than anything that's gone down. So this isn't geology we're seeing. But at this point, the first of the reflected waves has got back up to the surface, and now you can see that the first 4 traces on the left hand side have got a reflection signal. And now the second of those wavefronts has got to the surface, and we can see some more reflected signals at the bottom of our section. Even in this very simple animation that I'm using here, the picture rapidly becomes very complicated. And this is the final position that we have. Looking at the section on the right, the uppermost set of events are the direct arrival. Below that, there's actually a reflection from our first reflector, and below that, the reflection from the second reflector. But actually, the one you see below that is a reflection from some of the steep beds on the right hand side. What you can see here is that we do see all the reflections, but they're all in the wrong places. We have a distorted image of the subsurface now. Not only is the image distorted, but in reality we wouldn't see anything quite as sharp as this. I've drawn these reflection events as fairly short, sharp events, but in practice they will be smeared out a little bit and would look more like this. It's now getting very hard in some places to see the individual reflection events. They're all starting to merge in with each other. Another problem is that in reality the data would be very noisy. It might look something like this. So this is a more realistic simulation of what we will see in practice from a real seismic survey. This is our data, and it looks nothing like the geology. Somehow we have to turn it into a useful section. So we have to turn what we have on the left-hand side, which is called a shot record, into what I showed earlier, an interpretable section. In order to do this, we need to move the reflection events around so that they're in the right locations. We need to sharpen the reflection events so that we can see closely spaced reflections. And we need to try and suppress that noise. Those three things are what we do in seismic processing.